In this series of videos, we're going to be looking at the relationship between kinetic energy and chemical reactions, starting with kinetic molecular theory, which I will abbreviate as KMT from this point forward. The first two principles of KMT are pretty straightforward. Point number one is that all matter is composed of particles, which can be molecules, atoms, or ions, but it is the interaction between these particles that leads to chemical reaction. Point number two, all particles are constantly moving as long as we are above an absolute zero temperature. From this, we can come up with some fairly common sense statements about the relationship between state of matter and the rate at which particles move. Most people understand that the water molecules in water vapor move faster than the water molecules in liquid water, which in turn move faster than the water molecules in water ice. However, if we want to come up with specific energy-related statements, we need to refer to the energy that is due to movement, which is, of course, kinetic energy. In fact, the word kinetic literally means moving. We can simplify this term by writing it as E sub k, which takes a lot less time to write, which is why I will refer to kinetic energy as E sub k from this point forward. Now, obviously, we can't do the same thing in physics in terms of doing a simple distance versus time experiment to measure which particle has a higher speed, because you can't see water molecules. So instead, we can use temperature as a benchmark to make claims about kinetic energy, because in chemistry, temperature is actually a measurement of the average kinetic energy of a group of particles that all have the same temperature. So using this, we can make the generalized statement that the kinetic energy of gas particles, such as water vapor, generally have a higher kinetic energy because they exist at a higher temperature than liquid water molecules do, which in turn have a higher kinetic energy than solid water particles, also known as ice. Now, does this mean that every single water vapor molecule everywhere has a higher kinetic energy than every single liquid water particle? Well, that answer is no, because each individual particle has a specific amount of kinetic energy, but the kinetic energy of one particle is basically impossible to measure experimentally, so all that we can do is use the average, which is represented by the temperature of a given substance. Now, we can use this information in order to understand the last part of kinetic molecular theory, that being collision theory. And again, this is not particularly difficult to understand. If we visualize an actual chemical reaction, so in this case, we'll take a look at the synthesis of NaCl using sodium metal and chlorine gas molecules here. Let's say that each of these particles is moving in the same direction as each other. Eventually, when they move in the same direction as each other, they are going to hit each other, or scientifically, they are going to collide. Now, even though sodium is a solid particles still have a small amount of kinetic energy associated with them, and obviously gas particles have a fairly large amount of kinetic energy associated with them. And just like in physics, when these two particles hit each other, some of that kinetic energy is going to be transferred between sodium to chlorine and vice versa, resulting in the synthesis reaction occurring. So in chemistry, it is this kinetic energy transfer that leads to a chemical reaction happening. In this case, again, this is a synthesis reaction. Using this idea, we can come up with a fairly simple relationship between the rate of, or the amount of kinetic energy and the rate at which chemical reactions occur. The more kinetic energy given particles have, the more likely these particles are to collide with each other, and the more collisions we are likely going to end up being. The reason why this is true is even if these particles miss each other, if they have a higher speed, even if they miss each other, the more likely it will be that they will eventually hit each other again, as opposed to if they are moving slowly. And the more collisions we have, the more chemical reactions we will ultimately get. This is very important for chemical engineers whose job is to maximize the amount of product we get from a given chemical reaction. So that must mean if we want to maximize the amount of reactions we get, we need to maximize the amount of kinetic energy that we get in order to increase the number of collisions that we can produce. However, nothing in chemistry is that simple, and collision theory is just one of those things. If we look at a more complicated reaction, here we can see the acid ionization of acetic acid here. For those unfamiliar with the way that this reaction works, we know that water is going to use one of its lone pairs to make a bond with the hydrogen on the acid here, thereby breaking this bond and turning it into a lone pair, as we would produce acetate, the ion that we show here, and producing H3O plus hydronium, which indicates that this is an acid. Now, this water molecule here is pointed directly at the hydrogen that we want to remove, so this water molecule is in a pretty good position in order to do this reaction. This water molecule, however, is in a very poor position to undergo this reaction because not only is it not close to the hydrogen we want to remove here, its negative pole is oriented towards the negative pole on the acid molecule as well, which means even if these molecules do hit each other, the repulsion force is going to push these two molecules away from each other. The conclusion we can reach about this relatively simple reaction here is that only collisions that are made in the proper orientation, where the different reactants are pointed in the right way to actually undergo a reaction using the proper mechanism, will result in reactions. It doesn't matter how much kinetic energy this water molecule here has, if it's not oriented to point to the hydrogen that we want to remove, no reaction here is going to take place. Hence why the relationship between kinetic energy, collisions, and rate of chemical reaction is, with a few caveats, proper orientation being the most important caveat. To conclude this video, I will make a simple reminder. Do all particles within a specific reaction system have exactly the same kinetic energy? Well, again, the answer to this would be no. Remember that temperature is a measurement of the average kinetic energy of particles. If we visualize this up here, even if this water temperature, let's just pick a number, is 35 degrees Celsius, does that mean that both of these water molecules have exactly the same kinetic energy? Well, that answer is no. It is possible that this water molecule here is actually moving a little bit slower than this one up here, which would make it less likely to react. So the topic of the next video is talking about trends that occur not just with the average kinetic energy, but trying to help us visualize how important the individual kinetic energy of individual particles is.